Hey, Rafa. Can you hear me?
Yes, you can hear it pretty well.
Okay, great.
I cannot see you.
Oh, yeah, sure. But let me first try to
Yeah. Now you're.
yeah. Let me try to share the screen, see whether it works properly. This one, right?
Yeah, perfect. Yeah. Yeah. We're just waiting people arriving both electronically, online, and here at the room. So let's wait.
Yes.
But yeah. You have 5 minutes to take water or something like that if you want.
Yeah, no.
I'll turn off the mic.
Yeah.
And use. Are you hearing this, Yachi, again?
I can hear.
We can hear. Well, we saw. I don't know. Yeah.
Já tá gravando.
Beleza. Vocês querem? Pode começar as duas? Okay, so today on our seminar, we have the pleasure to receive Yachi Chu. Yachi is a Stanford PhD student in the math department, and I have been working with her since March of this year when I was at Stanford during the first semester. So she represents something that we have been working on. It's a work in progress, and we would be very happy if you can give some questions or some guidance. It will be so. Yachi, you have 40 minutes, so 50. It's up to you. Okay.
Okay, yeah, sounds good. Okay, so thanks for the nice introduction from Rafa, and thanks for having me here. I'm really happy to share this ongoing work with you. So this is the joint work with Rafa when he was he visited Stanford, and then a joint work with my professor Madeline Udell at Stanford. Okay, so today I'm going to talk about the Nystrom precondition interior point proximal method of multipliers. And let's get started. So the motivation comes from the fact that data-driven models are now ubiquitous in different applications, such as support vector machine, lasso, elastic net, and quantile regression. All of these are data-driven model. So it involves very large data. And we know that this problem, some of this problem take the form of a smooth function plus a non-smooth regularization term. And then there are some very good first order method which can be applied to solve this model, such as FISTA. But for the first order method, we all know that it's fast, but sometimes it suffers from the low precision. But this model sometimes can also be reformulated as either a convex quadratic program or a linear program. In that case, then we can apply second order method to solve it. And the second order method is slower for sure, but it can provide like higher precision for this model. So in some application, we might want that because, like, let's say in medical data or something, we might want to be a little bit more precise so that like result is more stable. So in this talk, we are going to basically focus on the second order method, and actually what we want to do is we want to accelerate the existing second order method using some randomization technique. So we know, I think it's well known in the optimization society that the state of the art second order method for solving convex QP and LP are interior point method, IPM. And then in each IPM iteration, the bottleneck is actually solving one or two linear system. Depends on like whether you use some particular character strategy, something like that. And for the large scale problem, the inner linear system in IPM is also very large. So usually we don't want to use the direct solver to solve this, such as like Cholesky factorization or other like the generalized Cholesky factorization, because it requires us to store the whole matrix, which is very memory consuming. So people usually use like iterative linear solver for the large scale problem, which need only the matrix vector product of the matrix. Okay, but the problem is the iterative solver really like suffer from the ill condition matrix, and that is the case for IPM method. So in IPM, the linear system will get like more and more ill condition when the result get closer to the optimal solution. This is also a well-known fact. So preconditioning is required. There are a bunch of like literature talking about the preconditioner in the IPM method, but most of them like talking about, most of them focus on the sparse constraint matrix. But we know, actually for the data-driven model, when we try to formulate this model into either convex QP or LP, the constraint matrix usually has some dense block. And this dense block is actually come from the data set itself. So let's say we have some image data set, then usually the image data set is like 100% dense, right? But the good thing is, this is the paper by like my advisor. So they found that like actually for the data matrix or like the dense block, it's probably have some Lorentz structure. So which means that we might be able to use the Lorentz structure to tackle this problem. And the randomized numerical linear algebra, which is abbreviated as RAND-NLA here, can help us like construct a good Lorentz approximation. So this work is like we try to use the randomized numerical linear algebra to find some Lorentz approximation, which might help us to accelerate the interior point, the original interior point method. Okay, so this will be our agenda for today. So first of all, we will talk about some kind of Lorentz approximation we call randomized Nystrom Lorentz approximation. And then we will, based on this approximation, we will talk about how could we construct the Nystrom preconditioner. And then we will briefly talk about what do we mean by interior point proximal method of multipliers, and then show some preliminary result in the end. Okay, so let's get started. Any questions so far?
No, it's okay.
Okay, so yeah, we can get started. So the Nystrom approximation is this approximation is basically defined for positive semi-definite matrix. There are definitely some version of like the approximation to indefinite matrix, but like the one for the positive semi-definite matrix has better guarantee, error guarantee or something. So yeah. And then So the approximation is defined with respect to some task matrix here, X. And X here is an n by L matrix. So L is less than n. So X is actually a tall matrix. Usually L should be like much more smaller than the size of the original matrix. And the Nystrom approximation of n with respect to this small tall matrix is defined as this. So it might be a little bit weird to at the first glance of this form, but if we if we remember the formula for the orthogonal projector onto the subspace, then actually this Nystrom approximation can be written as like you did some orthogonal projection onto the range of n to the half on the subspace spanned by X. So we have a like L dimensional subspace in Rn, which is spanned by X, and then we apply n to the half on it. But the range of like the n to the half is actually the same as like you apply n to X. So like you can understand it as like this is projection to the range of n on the subspace of X, and then you conjugate it by n to the half. Okay, so it's like you kind of do some projection here, and then this is like known as the Nystrom approximation. It was originated from like some PDE computation, numerical PDE stuff. So it has some property is worth to mention here. So first of all, as we say, because we did the project, we see that like it depends only on the projection of n onto the subspace spanned by X. So if we have like two X, X1 and X2, they have the same range, then after reacting n onto this subspace, they will have the same, like you will get the same orthogonal projection. So the Nystrom approximation only depends on the range of X. And this form tells us that the Nystrom approximation is positive semi-definite. And then because we did the projection, so the rank will decrease. The Nystrom approximation has at most rank L in this case. Basically, like how many? I mean, what is the dimension for X? It's on. I mean, yeah. Okay, and the third thing is the original matrix n minus the approximation must be positive semi-definite. So it kind of tells you that like the Nystrom approximation approximate the matrix n from below. So in particular, we have the fact that every eigenvalue of the approximation is less than or equal to the original eigenvalue. Okay, so this is some basic property of the approximation. Okay, the question is, how can we choose X? So this is where the randomized come in. So until now, we don't have any randomization here, and the randomized comes in for this X. The idea is we take X to be a random task matrix. So to form the Nystrom approximation, which will be known as like the randomized Nystrom approximation. So we need to determine the sketch size or the target rank L, which is like the number of column of L, number of column of X. And then for X, we just take some IID, each entry of the task matrix is an IID Gaussian Gaussian random variable. So there are some other possible choice for this, but in this talk, I think we can just fix it as like IID Gaussian matrix, because like other random matrices, sometimes it gives you some like advantage for computation, but the practice performance is like not really different. So people usually just take it as Gaussian IID matrix. And then The next step is we could compute the sketch of n onto this omega. So n times omega, we in the literature, people call it sketch because it's after applying onto omega, this become a smaller matrix or like a tall matrix now. And then some simple substitution suggests that the Nystrom approximation take this form, which is like the sketch times the pseudo inverse of omega transpose times sketch, and then times sketch transpose. So we can observe that like this formula depends only on the sketch of n. So this is a good thing that people will exploit in the literature. So why the Roland approximation depends on sketch is like important. We can think about like in some application that like the streaming model is one of the important application. So think about the case that we have an matrix n, and then like the matrix n is actually like has some linear update, like it was updated every moment, but it was when you update it, like you have to disregard the original. I mean, okay, that's putting it this way. So let's say n is the sum of several is the sum of some matrix h1 plus h2 plus h3, and then each of the time only hi is revealed. And then at every moment, you need to disregard the original, the previous edge. In that setting, we call it's a streaming setting. And then in that setting, we cannot store edge, but we can like compute its sketch and then update its sketch on the fly. And then with the sketch, then we can form the approximation for the original matrix, which is like why people consider the sketch instead of the whole matrix. It's usually like for some different setting. Okay. And so depends on the sketch actually means that it depends only on the matrix vector product of n. So it is kind of matrix free. We don't need to like have the whole matrix n. You just need to know like how to apply the matrix multiplication, that matrix vector multiplication. That's enough. Okay. So this is the property of Nystrom approximation. And then here's the algorithm show how we can compute the Nystrom approximation. The only thing I want to emphasize in this talk, in this slide, is the output. So if we look carefully at the output line here, we found that actually this algorithm can automatically return the Nystrom approximation into the factor form. So you can think it as like, it actually gives you the eigenvalue decomposition of the Nystrom approximation. So this is a good, good property that we will use later to construct our preconditioner. Okay, so this is an important feature. So U here will be like, you can understand it as like the approximate eigenvectors. Well, we have L eigenvectors, they are orthonormal to each other. And then the lambda hat here is a diagonal matrix. So like you only need to like take it, you only need to store its like diagonal vector, which has length L. Okay. Okay. So how good this approximation is? We have we have some error analysis here, and it's worth to mention this theorem a little bit to let you get more sense about like how good this approximation is. So this bound, this bound actually we call it is like priori error analysis, because the bound here involve the true eigenvalue of n, which is not in practice, which we don't know, because like we don't know the eigenvalue of n, but it's just like some theoretical bound. Okay, so let's look at this theorem together. So n is a positive semi-definite matrix again, and then the eigenvalue is ordered from largest one to the smallest one. The sketch size let's say we take the sketch size of this special form, which is 2p minus 1, and p is some number, which we will like talk about later. And then we consider the rank L randomized Nystrom approximation. Then on average, taking the expression, on average, the error of the approximation can be bounded by this number. And this number, how could we understand this two number? So by the Icard-Young-Mirsky theorem, the first term is actually the first one is comparable to the optimal rank p minus 1 spectral norm error, which means that if we want to use some rank p minus 1 matrix B to approximate n, the minimum possible error we can get is actually lambda p, which is the p largest eigenvalue of n. This is by Eckhart-Young-Mirsky theorem. And the second term, similarly, it's actually the best like trace norm error over all rank p minus 1 matrix. Okay, so it's like the sum of eigenvalue from p to n. So this theorem tells us that if we want to get some error bound which is like comparable to the error of like rank p minus 1, we need to use a slightly large sketch size here. How much larger? It's like roughly like 2 times p. So L is like 2 times p minus 1. So roughly, if you want to get such an error term, you need to like kind of get a larger sketch size as a trade-off. And on average, you will get this error term. And the next question is like, this result only show you on average, but is that a typical like result you will get when you have when you like in practice, like in practice, we only did one time, right? So we didn't really take a average, but is this a typical behavior of the Nystrom approximation? The answer is yes. This is because like the fact of like the random matrix called concentration measure, which kind of a little bit similar to the idea of like Chebyshev inequality, which saying that like the probability is kind of controlled by the expectation. So with this kind of result, we actually can also get some high probability bound for this approximation. For this error term. So although like we express the theorem in expectation, but like it's kind of a typical behavior you could expect in practice. Okay, so this is like this is like what is Nystrom approximation. Okay, so we would keep going, talk about like how do we use this approximation to construct the preconditioner. But before that, is there any question about the Nystrom approximation? Okay, so we can move on. So how could we use this to construct the preconditioner? So let's say we focus on this regularized linear system. Again, we have a PSD matrix N, and then we have some regularization term delta. We want to solve like N plus delta X equals to B. So we want to solve for X. This is positive definite. And then when we apply conjugate gradient, we can apply conjugate gradient to this system. And then usually you need preconditioning for very ill condition N. And by preconditioning, we can just think about like the goal like this. We want to find some matrix P such that P simulates the matrix N plus delta here. And then P is easy to invert. So this is like the goal to find a preconditioner. You can just understand it as this sentence. So let's think about some ideal case, which is like we have some Laurent, the best Laurent approximation, and then how could we construct the optimal Laurent preconditioner? Okay, so suppose we have the matrix we want to involve in the system is N plus delta, which we abbreviate as N delta. And then let's say the N delta, this is the best rank L approximation of N delta. Okay, so this is actually, I mean, by the Young's theorem, the U here is actually the first L eigenvector, and then the lambda L is actually an L by L diagonal matrix consists of like the L largest eigenvalue of N delta. Okay, it's by Young's theorem. I mean, there's no like mysterious here. Then we claim that with this kind of information, U and lambda, then we can actually construct the best preconditioner as this form. We will like, I will explain in the next slide why P star take this form, but I want to show a picture first. So actually, like when we do the preconditioning, what this preconditioner did is like this. So N delta is very ill conditioned. So it's like its condition on its spectrum might look like this, like the blue line like here. It decays kind of fast. But after the precondition, after we applied such kind of ideal P star preconditioner onto N delta, then it flattened the top eigenvalues of N delta. So the spectrum after the preconditioning, the spectrum will look like this. So which is like you have a flat spectrum, and then the same spectrum as N delta. Okay, so you see that like the original condition number is this number divided by this small number, maybe like 10 to the 10 divided by 10 to the -1. But now after like preconditioning, you maybe flat the top eigenvalue to like 10 or something. Then the condition number decrease a lot by like 10 to the 9 factor, something like that. So in this case, we also see that like if the spectrum decay very fast in the beginning, so basically means that your matrix have good low rank structure, you only have like several rank, and then all the other like eigenvalue are very small, then we can expect that like you can improve the condition number by a very large factor. Okay, so that's go to next slide to explain why this like preconditioner take this form, and then after that we might be able to understand why we have this kind of picture. So this is like our best low rank approximation, and then this is the preconditioner we take. So it can be separated. I mean it could be understood by separating it into two terms. The first one is actually describe the action onto the subspace spanned by UL. I mean remember that U is actually the first L eigenvector. So basically it's it's a subspace spanned by the first L eigenvector. So the action of N delta is easy. I mean, it is exactly described by this lower approximation because it basically tells you that in each like eigenvector direction, how much you need to scale it, and then put them together, you get like your linear operator N delta onto this subspace. So if we want to find some P such that like P is kind of simulates the N delta, what we need to take is exactly take P star has the same action as this N delta or as this like approximation on this subspace. So we see that like for the first term we take exactly the same action or like the same approximation here, and then the scaling here is not a big deal. It just try to make the condition number to the top eigenvalue to be closer to 1. So don't worry we don't need to worry too much about this factor. It's just some factor which give us like optimal condition number, something like that. But how about, so we already defined P star for this space. How about its complement? We also need to define the action of P onto the complement. And the complement here is actually can be written as identity minus UU transpose. So it's actually the range spanned by identity minus UU transpose. We need to write in this form because we want to basically use the information of U from here to express this space, to express the complement space. Okay, so we get no information from our low-rank approximation, even though it's the best low-rank approximation. We have no information to the action of N delta on the complement. So we just take P star as identity onto this orthogonal subspace. Okay, so the second term we just put identity here. This means that this is just like the space spanned by the space of complement, and then it's the identity. So this is the component of this preconditioner. Okay, so with the low-rank approximation, we know this gives us like the kind of optimal preconditioner. We didn't prove that, but try to give some like idea of this. Okay. Any question about how we construct this P star so far? Okay, great. Yeah, so now we can come back to think about our cases. In reality, we don't have the ideal low-rank approximation, because like it involves like computing either eigen decomposition or the SVD decomposition. So but we have like nice from low-rank approximation, so we can still do something here. Instead of finding the low-rank approximation for the whole matrix N plus delta here, it's better to find the low-rank approximation for N, because like we want to exploit this kind of structure, and then like this plus, basically this representation is very good. So we will only consider the low-rank approximation for N, which we write as like U lambda U transpose. And then the N plus delta, you just simply like add the delta I to the diagonal of lambda, then you get an approximation to N. And this approximation is usually better than the approximation you got for the whole matrix, because you kind of exploit this kind of special regularized structure. And then following the same idea as we mentioned before, for the optimal low-rank for the optimal preconditioner, we basically just use all the information we have, low-rank information we have, to construct the preconditioner like this. Okay. The only difference here is worth to mention is the lambda L plus 1 in the optimal preconditioner, but we only use the L largest eigenvalue for our preconditioner. Why this is the case? This is not a typo. This is the case because like optimally we want the L plus 1 largest eigenvalue, but we don't know that information in practice. So we just take the closest number to that. So we put it here. And then the inverse of P is also easy, because basically like you have two subspace, and then for each subspace, you just do some scaling stuff over each direction. So to do the inverse, you just along each direction, you just redo the scaling stuff. So this is like inverse of the diagonal matrix, and then this reciprocal of this number is just like you redo the scaling, and then you get the inverse, right? And then for the identity, for the complement on the complement space, you just, because it's identity, so like the inverse of identity is again identity, so you just put it here. Okay, so some features worth to mention a little bit. So first of all, when we construct the preconditioner, we only need the matrix vector product of N. Why? Because to construct the preconditioner, we need only the Nystrom approximation. And the Nystrom approximation relies only on the sketch of N, which can be constructed by the which can be constructed only through the matrix vector product of N. So this is one feature. And another thing is, if we take a closer look to this P inverse, we could find that it's easy to, it's cheap to store and cheap to apply, because we need to only store the smaller matrix U, which is n times L, and then we only need to store this diagonal matrix, or we just need to store the diagonal entry, which is a vector of length L, and then a scalar delta here. Then we know all the information of P inverse. And then to apply the matrix vector product of P inverse onto some vector V, we just like apply the matrix multiplication sequentially. So it takes only like big O of n times L flops here, which is better than like which is better than the O of n squared. And then this preconditioner is positive semi-definite, so it can be directly applied to CG. CG requires the preconditioner to be not only symmetric, but also positive semi-definite. Okay, so
Actually, just say something here. Even for constructing the Nystrom preconditioner, even though you have to make a spectral, find the spectrum and all that, you can do that by Lancho. So it's also match back. You just apply the matrix to the vector. It's just matrix to vector multiplication. So even when you are computing the lambda and the u, you are doing it in this way.
yeah, exactly. So you apply it basically like kind of sequentially, right? Yeah, exactly. So the multiplication is also like not very like expensive. Okay, so yeah, we can see an example for the Nystrom PCG here. So let's look at the model of ridge regression, which is basically minimize some least square term plus some 2 norm regularization term. And then by taking the gradient, we know that the solution to the minimization problem here is satisfying this linear system. So we can use Nystrom PCG to solve this linear system. Okay, and then we will see that like Nystrom PCG actually dramatically accelerate the solution of that linear system. So we take G to be some data set called shuttle with random feature, which has dimension like roughly like 43,000 times 10,000. And for the rank for the Nystrom approximation, we take 800. Then this plot shows the residual of the Nystrom PCG. So we see that like CG stalls, here, but the Nystrom PCG can goes down to like, I think it's machine precision in certain iteration. So yeah, so in this example, it's kind of very successfully accelerate the linear system solver. Okay. So yeah, so this is the idea of Nystrom preconditioner. Is there any question on this preconditioner? Because this is the main, I think this is the main part of this talk here.
No, you can go.
Okay, cool. So so let's briefly talk about like the IPPMM method. I think like most of the thing here, I would just talk about it briefly. Most of the thing here is should be not too different from the planned IPM method. I just want to make sure we are on the same page. So briefly talk about this. So the IPPMM, in one word, is a combination of interior point method and proximal method of multiplier. And by the way, it's a recent, really like recent like algorithm proposed by Professor Gonzio and his collaborator in roughly 2 years ago. Okay, so it's a variant of IPM. And again, the same as IPM, the target problem for this algorithm is to solve linear constraint convex QP. So minimize some convex quadratic function subject to linear constraint AX equal to B with non-negative variable X. Okay. And then the idea of this algorithm is like this. It tried to exactly solving a sequence of subproblem. And this subproblem comes from, this subproblem are actually the PMM, the subproblem in the PMM method, original PMM method. So the original PMM methods involve solving this problem. And then this problem is parameterized by several parameters. First two are the delta and rho, which are regularization parameter. And then it also parameterized by the lambda k, which is an estimate for the Lagrange multiplier corresponding to ax equals to b, corresponding to the constraint ax equals to b. And then the third thing is zeta k is the estimate for the primal solution. So in the PMM method, we have this the subproblem parameterize this. And IPPMM want to exactly solve this sequence of subproblem. And how? It is by IPM. It is every time we just apply a few iterations of IPM to solve this subproblem exactly. And then after that, the parameters, all these parameters are updated. And then the new subproblem is solved exactly by IPM again. And then so on and so on. And sometimes I think usually the IPM we apply here is usually one iteration or so. So it's not a lot. Okay. So so how could we how do we mean by apply the idea of IPM to solve this problem? It's just if we use the logarithm barrier idea from IPM, then it turns out that the Lagrangian we want to solve is the objective function minus mu times this is log of xj. Okay, so because the non-negative constraint here. So if we take gradient equals to 0 and then introduce some new variable, it turns out that the system we need to solve look like this. And then this, if you look at the black part, it is just the perturbed KKT system that appears in the original IPM method. So this is dual infeasibility, primal infeasibility, and then this is complementarity condition. And then the mu k here is some greater than 0, positive value, such that you do not need to solve exactly the complementarity problem. The difference is we have additional regularization term here, which is why IPPM different from the original IPM method. And then to solve this slightly nonlinear system because of this term, using the IPM idea, we just apply Newton method to solve this. And then after some standard what's that? The derivation, the Newton step can be obtained by either solving augmented system like this or the normal equation like this. So this is quite standard. This two system is standard in IPM method, except that we see that we have two regularization terms here. One is rho, one is delta here. But in the literature, this is also not, this kind of modification for the IPM is known as the primal dual regularized IPM. So IPPM is actually one variant of primal dual regularized IPM. The only, the most important feature is that they claim that this is the first polynomial time complexity regularized IPM. So for the regularized IPM, we don't have polynomial complexity result before, but this is the first one they mentioned in the paper. Okay, and just a quick remark here. So how to, we need to solve either, we only need to solve one of this system. So how do we choose this? So we usually want to solve normal equation because it involves a positive semi-definite matrix, but the augmented system is indefinite. So we usually want to solve normal equation. But the thing is, there is an inverse here. So to solve this normal equation, to use this normal equation, we actually need Q to be have some good structure like diagonal or Q equals to 0 so that this inverse is accessible, then we can like use the normal equation. Otherwise, we need to go back to the argument system. That is the principle here. And yeah, so now we can talk about like, we want to solve this to linear system, how? And then again, because the problem is large, so we want to use iterative solver. How do we do the preconditioning? So let's denote, again, we denote now the first part of the positive semi-adaptive matrix. We call N previously, so it take this form A times some diagonal matrix times A transpose now. Okay, so large scale problem, we cannot form this N directly. Basically, we don't want to multiply out A times D times A transpose. So we should not use the direct solver here. We want some matrix-free solver for that. And then the most important matrix-free solver here is the precondition CG. The question is only like, how do we do the precondition? And again, just want to remind us that like, for the data-driven problem, the matrix A usually has some dense block, right? So there are some like usual sparse preconditioner in this context. Probably like people will use incomplete Cholesky, but that is not suitable for this case, okay? Because A has dense block, and the incomplete Cholesky basically means that you have a sparse matrix A, and you try to do the Cholesky factorization to this matrix, but you want to keep the Cholesky factor has the same sparsity as A. So you just ignore all the fill-ins when you do the Cholesky factorization. Okay. But so we want to use the Nystrom preconditioner because it really fits into this context. First of all, like it's matrix-free, you only need the matrix vector product of N. And then secondly, like the dense block might give you some Lorentz structure. And then the Nystrom preconditioner, it exactly exploit the Lorentz structure of the matrix. So yeah. So that's why Nystrom preconditioner fits into the context. Okay, so we can look at some preliminary result here. Okay, so before I directly show the result, I just want to quickly mention a little bit about the details, implementation details here. So when we run our algorithm, we not only like accept non-negative variable, we also accept like free variable and box constraint variable like this. This can help us to like introduce additional variable, because like if you have free variable and your algorithm only accept non-negative variable, you then need to write the free variable as like x equals to x plus minus x minus, which will increase your problem size again, which is not good for like large scale problem. And so it can keep the normal equation as the same size as the number of A instead of introducing new variable. Okay. And then of course we use the predictor corrector method for IPM, which helps the convergence of IPM. The thing is, when we apply the predictor corrector, the two linear system we need to solve, we have two linear systems to solve in each IP PMM iteration. They share the same matrix, left-hand side matrix. So we can use the same preconditioner. So only one preconditioner we need to compute the preconditioner only one time in each IPM iteration. And it can be used for two linear systems, which is good. And then we also design some intuitive adaptive sketch size strategy, which I don't want to go to details here. And then the initial point is the standard Merrill trust initial point. And we stop our algorithm when the relative infeasibility and relative optimality gap get to 10 to the minus 4. Okay. So, okay. And then in our result, we use some real data set from UCI or libSVN or some neuroimaging data online. So this is the data set we test. It contains like some wide data set and also some tall data set. And then this is ordered from dense data set to very sparse data set. We will see like the performance of like neural approximation on a sparse data set as well. Okay, although like we don't expect is a very good choices. Okay. Okay, so the first example we want to look is the simple vector machine, which is actually for a classification problem. We have X is a feature matrix, Y is the two-class label vector. And then the dual problem for L1 SVM is this QP. We have the free variable here, and then we also have the box constraints here. So which fit into our like format of our algorithm. Okay. And in this case, the normal equation will have size features plus 1. Okay. Okay, so this is the result here. So we compare the Nystrom preconditioner and no preconditioner here. We can see that except for this problem, it's not too bad. So without the preconditioner, most of the data sets can still converge, except for CIFAR 10, it cannot converge. The algorithm stalls here. And then we can see that for this STL10, which is like one of the, I think it's the largest data set in our task. No preconditioner will require one more outer iteration, while like the Nystrom preconditioner has, one iteration less. But in terms of time, Nystrom preconditioner can give us like a huge improvement, because like most of them is like more than half by a factor 1/2. Okay, but if we look at the following 3 data set, they only have the comparable time for the Nystrom preconditioner. It's because like this data set, as we expected, they are more sparse. So they're not like we didn't get a dramatically acceleration, but it's not like it did not slow down the IPM very slowly. So this is kind of, this choice is kind of robust here. Okay, so we also try to compare the former example demonstrate the effectiveness of Nystrom a preconditioner in IPM setting. We now try to compare with other like preconditioner in matrix-free IPM. And one standard like preconditioner is partial Cholesky, which means that like we don't do the full Cholesky factorization of the matrix N delta. We only like do L stack of the matrix. So we get L columns of Cholesky factor. After that, like we only have like some pivot. The L largest pivot we have from doing the Cholesky factorization, and then the remaining stuff is actually the shared complement. But when we really put this algorithm into like the implicit process setting, we won't compute the whole shared complement at the same time. We will only compute the diagonal and some selected column of the shared complement. So we cannot really like have all this information here. The information we have here is only the L columns of Cholesky factor and the largest pivots, and also only the diagonal of S. So the precondition we choose is basically this form, except the S here is replaced by its diagonal, because we won't compute whole shared complement here. Okay, this is the another like kind of standard preconditioner people might use in the matrix-free setting, and we try to compare this preconditioner with Nystrom preconditioner on this model. So this is a regression model for, again, the least square term plus some L1 regularization term plus L2 regularization term. And then this problem can be formulated as QP as well, with some free variable and non-negative variable here. And now the normal equation will have, it's more challenging because like it has size n plus n. Okay. Number of instance plus number of feature. So we try to compare this. But currently, currently like our implementation for partial Cholesky is still like a little bit too memory consuming. As you can see, like it takes much more longer time than the nitrom preconditioner. So we kind of suspecting that we didn't do the like implementation very good in a good way. So, but so I think we still need to improve the partial Cholesky implementation, but we can still see that this stuff, like when the problem is very large, so MRI dataset 1 is larger than MRI dataset 2, and we see that like in the partial Cholesky case, we did have one more outer iteration here. So which is like we see that like kind of saying that the inner solver is kind of limited here, although the sum of inner iteration is smaller, but it's take away like way too much time. And then for this data set, it cannot converge after like 30 hours or so. So yeah, so it's so we this is just a preliminary result. We are still trying to do a fair comparison between our preconditioner and the existing preconditioner. Okay, so yeah, so that's basically like our talk today. I will like briefly mention the next step. So for sure, we need to improve the implementation of partial Cholesky preconditioner, and we want to come up with some better adaptive sketch size strategy, because it's a parameter which user needs to specify beforehand, which is not easy to take. So it's like parameter tuning problem. And then we also want to design some randomized preconditioner for the augmented system. As I say, augmented system is an indefinite system, which is a little bit more complicated, but it is possible to precondition the augmented system using the information of using the preconditioner from normal equation. So we have the nitrom preconditioner for normal equation. We kind of want to put that into this setting. So this is our next step as well. And then also we want to test our algorithm onto other different problems, other data-driven problems, such as like portfolio optimization, or we want to try the LP relaxation of MILPs, mixed integer linear programming. Yeah, so this is our ongoing work today. So a lot of things going on now, and thank you all. So obrigada. I'm not sure how to pronounce it, but yeah.
Okay, thank you, Yachi, for your talk. Very instructive and clear. Maybe we can do that.
Yeah, thank you.
Well, we have some time for questions, comments.
I have
Two.
I found very interesting the idea of this conditioner using randomized matrix. I think it's a very good idea actually for some cases. But this choices examples to choose, they sound a little bit weird to me. I will try to explain myself.
Yeah.
So first, this is talking more about, I didn't know that also and browsers work. The interior point proximal method of multipliers.
Yeah.
But the proximal method of multipliers, it has linear convergence rate.
Yes.
Okay.
Yeah.
So the reasoning that you're going out of theta because theta is only first order. Because we want to do second order, but then when you put the second order as a to solve the third problem of something which is linear convergence.
Yes.
For me, it loses the appeal.
I see. I see.
You see? Because you don't have any guarantee that your test is going to be fast conversion and it's going to get you very high accuracy.
Yeah, you're right. You only have linear conversion.
You only have linear conversions.
Yeah.
That's one of my points.
Yeah. I can say that we choose, Madeline had this idea of using randomized recognition or on IPN or something. And I came up with this with this method of Jacek. And it is good for our case because the means from precondition needs the regularization for the delta plus something to be well behaved. And the usual IPM doesn't have. So that's why we choose this one. Okay, so it fits our precondition, and then it works pretty well on practice. But you're right. You're right. Sorry. Yeah.
That's one of the points. And the other points that if you look at the slide where you had the original QP,
Yes.
and then you apply this is not yours, this is
Yeah. Yes.
and then you apply the proximal method of multipliers to that problem.
Yeah.
It's not clear to me why don't you dualize also the x bigger than 0. Because once you do that, the subproblem is going to be only to solve a linear system, right?
Yeah, but you will have to at least project, right? No.
No, because you have multipliers to drive x.
Yeah, but you have to choose the multiplier, right?
But as you have to keep the multiplier for the other traits. So why don't you only the linear quality constraints?
Yeah, I guess.
To dualize, and you don't dualize once you're doing augmented logarithm. It's not obvious. Why you don't dualize the positive constraint? Because then your subproblem is going to be simpler in that case, because each subproblem you can solve exactly.
Yeah.
With a single linear system, if I'm not mistaken.
Yeah, I see.
Actually, using a paper conditioner, probably.
Yes, yeah, I see.
But I think that.
Yeah, that's a good idea. Yeah, maybe that's an idea. Yeah.
Okay, so it was not clear to me why that choice was made by the outset.
That's a good idea.
Huge.
That's a good
We
question.
need to look at the details.
Yeah. Yes, but it's a good question. Very nice question. Yeah.
And a final remark, I have worked a lot in Lasso and Elasticnet and things like that. And for those kind of problems, you have some methods that are based on the spectral step,
Okay.
the Buzz-like boring step.
yes.
I like to solve Buzz-like boring by the step.
Yes, of course.
And like the Sparta method from Wright and Figueiredo for the case of Lasso.
Yes.
But it's exactly the same idea works for ridge regression and elastic net. You can do the, and all those methods, they will behave like you cannot prove that, but they will have like first, second order conversions in many cases. So again, and the third problem in that case will be only solving the systems or something like that, not even that. So again, it's not clear to me if those choices like examples are good choices because there are other fast algorithms. Even the SVM, I have an implementation that this is kind of idea.
Yeah.
Where you're doing a spectral method and you have to project the spectral projected method, and the projection in that case is projected into a simplex or something else like a simplex, a single constraint and the positive order, something like that.
Yes, you're right.
And you can project that step very efficiently. I have an algorithm for that actually. So
Yeah, you're right. I think we
so the example they are a little bit.
Yeah, what you mean here, like, is maybe we should look for problems where you really need the convexity Right.
You really need
to use IPM.
to use idea.
Yeah, I see.
Because it's not clear to me that in those problems, the IPM is a natural choice.
I guess.
And for each one of them, we have a specific algorithm that should be better suited for that. And then you say, I'm going to solve this in, I don't know, 500 seconds. And then somebody comes and, oh, no, I can solve that not a problem in 10 seconds.
Yeah.
Because I'm using specifically
Yeah, you're right.
for that class of problem, see.
Yeah.
And I could see that pitfall in many examples.
Yeah, you're right. You're right.
Yeah.
Yeah, that's a fair assessment.
Okay. So
Yeah.
sorry for the long. Oh,
No, but
Yeah,
it's good because we're trying to write. The idea is that we want to use an interpret conditioner for IPMs, right? So what problems do we have that are suitable? We need data-driven problems. So
Yeah.
that's what we're looking for. You're right in the problem. That's still ongoing work and
Sure.
first preliminary tests that we have kept us confident that this, if we have like a good test set, it will be a good without reading.
Yes. Yeah, I think like one of the main thing I didn't mention in the next step is like we are still trying to find a better like application of this like algorithm. We need better like test example here basically, because we don't want to use the simulated example, but yeah, we also try to find some minimal meaningful model in our setting. Yeah.
Okay.
Thank you.
Thank you. Any comments? Yeah, we have for the last question or comment. If not, let's thank again, Yachi. Yeah.
Thank you.
Okay, see you next week, right? Yeah. Yeah, thank you, Yachi. It's very good.
Thank you, very good. Very good.
Bye.
Thank you.
Thank you.